This last case study is an Ingersoll Rand condenser. There are two condenser shells running at a common pressure. Each cell has two bundles, each with a dedicated air offtake line. This unit operates with three RheoVac probes. One probe is installed in the common, and the other two probes they allow to be moved between the four other vent line locations. For this leak audit, a fourth probe was installed and the common probe was moved so that each vent line 1 through 4 could be monitored. This plot shows the air and leakage for all four vent lines, which are summed up to get the total unit air and leakage. The first half of the plot shows the conditions before the leak is located and repaired, including the amount of air and leakage being measured in each vent line. The total air and leakage is approximately 17 SCFM, with the majority of the air and leak contribution in the number 1 and number 4 vent lines, which accounted for 14 SCFM. The number 2 and number 3 vent lines show very low air and leakage. Based on the design of this condenser, the primary source for air and leakage in these two bundles would have to come from expansion joints or turbine seals, or from penetrations directly above the bundles on the water box side of the condensers, of which there were very few. So based on this data, we were able to conclude that there likely was very little leakage from turbine steam seals and expansion joints. This meant that the effort searching for leaks could be focused on penetrations in lines entering near the number 1 and number 4 bundles. Narrowing down the leak search area would have been impossible, leading to an arduous search process without having a probe installed in each of the vent lines. During the leak audit, a leak was found on a line that penetrated near the number 4 bundle. When the leak was fixed, you can see the air and leakage drop, specifically on the number 4 bundle, greater than in any other bundle, and leaving a total air and leakage of approximately 9 SCFM. The leak that was found was a sheared off pipe stub connected to a sight gauge on a feed water heater. This was not located in a well-traveled part of the plant and would not be noticeable without climbing a ladder to this specific platform. Plant personnel closed the valves around the sight gauge, and the air and leakage immediately decreased to approximately 9 SCFM. After the leak was repaired and the total air and leakage was dropped to 9 SCFM, you can see the mass ratio increase from 4 up to 9. Now, a mass ratio of 4 is still above the rule of thumb of 3, which means that there was no stagnant zone formation with the 17 SCFM of air and leakage. Now, with the mass ratio at 9, the plant was running 2 pumps. Now they can turn off 1 pump and run with only 1 pump with no increase in condenser pressure. During this presentation, I've shown the essential instrumentation we use to identify and repair air and leak sources. I've also shown how this instrumentation can be used to determine if the condenser problem is a vacuum equipment problem or an air and leakage problem. Using case studies and data to show how this can be done quickly and efficiently and recover potential loss generation from high condenser pressure. If you have any further inquiries or questions, please contact Mitchell Morrison at mmorrison@intechflow.com. That's mmorrison@intechflow.com or 1-800-743-6822. Thank you.